6:02 and we're going to start. This is the 20th instance, so a little anniversary with Pankaj Mehra of the Industry Spotlight hosted by Santa Clara Valley Section's Corporate Liaison Program that I chair and work on together with Shmuel, Paolo, Mary Baker, and Zoran. It is great honor and pleasure to host today Pankaj Mehra. Pankaj will introduce himself in a more eloquent and more detailed way. I just would like to share my past experience that he is one of the nicest people I work with in Hewlett Packard Labs. Also, with huge responsibility, he was always there to give advice, to take hard, responsible assignments, like leading the lab in Russia. He had tons of experience in storage that he has transferred into his most recent startup. So with no further ado, Pankaj. And if you can please all turn off your cameras while he's speaking, then turn back on when we ask the questions. Pankaj Mehra.
Thank you, Dan. It's so nice to connect with everyone and to take a little bit of your time to do what I do best, which is share what little I know with a lot of enthusiasm. So I'm humbled by some of the people who are here who know a lot more about memory than I ever will. And so first apologies for an aggressive title, but there will be a quiz at the end and you will be asked, how do you tame a wild thing like memory? And the picture will give you a clue that you will do it on the back of elephants. And, there is a little play there on the long memory of elephants. And we wanted to, when we started working on persistent memory and then persistent pointers, we wanted to recognize that. And so elephant's memory would have been too much to say. So we made it easy and said elephant's memory. But that's the play. And on the back of this software that we'll talk about, we want to conquer the wild beast that memory is. Okay. So that's all the symbolics on the slide. A little bit about me, and then we'll be on our way on the technical topics. I hope you see my screen well. So I, try to map sort of progress in research and innovation along outcomes of two kinds. One is traditional research outcomes, and then going sort of beyond what one person does to seeding ideas in teams, then having products form around them, incubation, startups, acquisitions, other forms of success, standardization, and actually having an ideological legacy where the idea does not die with you, but lives on and is picked up and is developed for a long, long time. Okay. The other axis is to sort of look at its impact on what is achieved as a result of working on an idea. So, not every idea and the combination of idea and person goes equally far. We are all limited in our own ways. But thankfully for me, I, tried many things. Like, early days, I started my thesis with at the intersection of computer systems and machine learning in the 80s. And then, took that work to very large scale systems at NASA, got interested in networks, did a variety of things like worked on InfiniBand Trade Association and contributed to InfiniBand specification in between, actually built some really interesting systems that, for example, got me an award from Jim Gray himself in person before he disappeared. But my first love was memory. And the first I recall working on memory is I had quit Compaq to go do an InfiniBand startup because Compaq had decided to stop building InfiniBand chips, and I was invested in it. So I went and followed my passion, and we were building some virtualization software on top of Fujitsu Red Switch and Mellanox switches. Okay, so a company called IntelliFabric. And so I quit about a month before the planes ran into the buildings in New York, and then the funding dried up. And so when HP bought Compaq and dangled a bunch of money and said, you come back full time, it looked very appealing. But when I came back, I did not want to give them my startup idea. And I used to be in the tandem business, tandem Compaq HP was my path there. So I wanted to come back and do something useful based on what I learned in InfiniBand, but not do network. And so I thought about it a lot. And our customers in those days were people like Target and America Online and London Stock Exchange, Chicago Mercantile Exchange, and so on, Royal Bank of Scotland, for example. And there was a problem. The problem was that there were these systems out there that were running, transaction workloads like order entry and order processing. And the system would be crawling to low throughput, but there was no resource in the system that you could measure that was fully utilized. And everybody was perplexed. What the hell was going on? Okay. And I kind of, had come from the system side at NASA and had taught at IIT and knew a little bit about scalable systems. So I knew there was some dependency or some deadlock that was causing things to happen. And so I focused on how long locks were being held by order entry transactions. That led me to the commit problem in transaction processing systems. And in 2004, finally, we wrote about it, an IPDPS paper, which was called Fast Persistence, the Magic Potion for Online Data Stores. And in this paper, we coined the term persistent memory. Okay, and we did many things with it. We actually built the persistent memory units. This was 2002. We wrote file systems that were stateless file systems that kept all their state actually in the persistent memory units. So it was actually fully tandem capable file system in which you could, remove any device, remove any piece of hardware that was running the software, and the system would initialize from the device, come up, and be operational without missing a beat. And we re-engineered Jim Gray's process pair. So one process in the pair remained and the other became persistent memory. And the backup could just come up anytime and its state was fully populated and could just go run. So, we developed log-driven storage controllers, which were like how Amazon eventually ended up building the Aurora system for their Redfish database. So there were many, many developments, and the nonstop system was rewritten about a few hundred lines of code. But when those few hundred lines of code in the audit trail and transaction monitor were re-engineered to take advantage of persistent memory, the NASDAQ level 2 trading system would run 3 times faster. It was just coming up, and we were seeing the first billion transaction days. This was 2002 to 2006 at HP. And then, I tried to start a company, but in those days, the VCs are a herd, and they were following the idea of e-discovery. So every time I would go to a VC and say, I have a technology for doing fast transactions, they would say, hey, does it do e-discovery? Can it speed up archival systems? And I say, no, this is for high-speed transactions. I said, not interested. So after trying a lot, I decided to open it all up. And I went and gave seminars to compiler people. So I visited every compiler group in the country. And I said, I could take persistent memory as far as I could with current generation hardware and software. And I realized that to get to load store persistent memory, the kind that we got later, 10 years later, we will need some good work on compilers to move loads up and push stores out so that we can take the higher penalty of stores that come with this territory. And the compiler people also ignored me, much like the VCs, and my work was done. So I moved to other parts of HP and then did this HP's dedupe engine, and then eventually ended up leaving HP. And uh, then in 2013, I landed back at Fusion IO. How that happened, because one of the board members of Fusion IO was Shane Robison, who was CTO of HP when I did the persistent memory. So cut the long story short, I ended up back in the flash industry and working on persistent memory using Fusion IO's capacitor-backed DRAM, and improving MySQL transactions. And then at SanDisk, we ended up building a ReRAM jointly with HP and government money, which was not successful. But then the journey took me to Western Digital and Samsung and other fun places where I did computational storage. And then, here I am at Elephance Memory. I'm still in love with memory and trying to build things. So let's talk about this memory thing, okay? What's going on and what's all the fun about. So rumors are that last year, memory went from being number 2 costliest thing in the data center to being number 1 thing in the data center, okay? The reason is, it was supposed to, if you were to believe Jim Handy, when I met him in 2015, he told me that memory was going to be 15 cents a gig by 2020, okay? Here we are, it's $4 a gig, and Micron is signing LTA with their customers right now, okay? Go figure, okay? So it's not only the costliest thing, it's actually in short supply. The bit growth is being outpaced by demand from in-memory applications. People are not dumb. I was looking at a presentation from Mnemonics from 2009, the company that is responsible for phase change memory, which later came out as 3D Crosspoint with some other innovations. They in 2009 had correctly estimated that it would take about 10 years to introduce this. But everything else they said about what that memory would be like was not as they predicted. But they knew, and it actually turned out to be true, that it takes 1 or more decades to actually bring a new memory technology to market. The less well-known secret about memory is that unlike logic and unlike software, where process is the leash that tames those technologies. So if you have good process around logic, you have good process around software, you can produce good product at a very regular cadence. Once every year, twice every year, you can just do chips and you can do many releases a day in software, as you know. Memory, you build it and then you find out what you got. So, in memory work, I did not know this until I went to work for the SanDisk fab, that there are these things called memory health team. So you build your, test vehicles or production wafers, and then you start to do health on them, and then you find out how bad is it. Okay, so it's like that. It's actually completely untamed. The other thing is that the computational models that we have, whether it is computational crystallography or other computational chemistry and physics that we need to model these things to predict what we will get, are grossly inadequate compared to what we need. So, when you're messing around with PCM, stoichiometry, or other things, you cannot just run science experiments in virtual way and predict the outcomes. You actually have to build things, you have to mix chemicals, you have to go work with, contaminations and other messy chemistry in the lab and equipment. And as far as making memory. So memory is ugly when it comes to its deployment. Its deployment style is what we call bespoke deployment. If you need memory somewhere, you have to deploy it there. This is kind of like, how servers used to be before VMware came along. I remember that, HP was in the business of selling to major providers at that time. And I remember that, people used to buy big servers, scale up servers for big workloads. It was not like you could assemble a big uh, uh, computing resource out of little resources. Uh, and then, virtualization came along and we could fit, do the tidal scale things or do the virtualization thing, carve out many little things out of a big one or make a big thing out of little ones using scale out uh, or distributed computing. But memory is not software defined. So we have software defined compute, software defined storage, software defined networking. There is no such thing as software defined memory until recently. It's hard to sell, therefore. Okay. So you put it, you look at the combinatorics of data center, 100,000 servers, many different SKUs. So, we hear these jungle rumors from data center customers that uh, we hear the jungle rumors that it's hard to sell. Okay. Why is it hard to sell? Because it is trapped in these combinatorial bespoke deployments. You have one kind of instance where memory is, and you're selling cores on another type of instance. Well, that memory is now stranded with that wrong instance. So it's not like memory is a fabric connected resource that you can dole out, as needed, or you can independently scale compute and memory. Now, John Shaw, who is the CTO at NERSC, and other people have been, talking to them, listening to their presentations. Turns out that after you sell it, somebody has bought it. Okay, so 75% of the time, an app will use only less than 25% of its provisioned memory. So then there is further waste after that, because why? Because not only is it bespoke deployed, you have to buy all you need upfront as a consumer. So the evil of memory is just profound, okay? And how profound is it, and what does it look like from a customer's point of view? So when I was in the memory industry, I knew we were selling memory into the data center, like I said, about $4 a gig. If you do the math by comparing a couple of EC2 instances, for example, that have identical everything, but only differ in how many gigabytes of memory, you will easily see that they sell it, actually rent it out at 22 and a half to $29 per gig per year. Okay. Now you do think about it, $4 a gig to buy it outright, but selling you at 22 to $29 for renting out for 1 year by the hour. Okay. This is a consequence of the two things to its left. It's not that it is just costly to buy. It's actually just so terrible as a resource in terms of how we use it and how we work with it, that cost for everybody is high. It's costly to buy, costly to deploy, costly to sell. And then as a customer of the data center guy, when you buy it, it's costly to get your money's worth. So, we started looking at it. And so how the current practice, right? It's as a device. So you attach memory to sockets. And so what's shown here is a cartoon cluster of 4 servers, which are each 2 socket, and memory is attached to the parallel DDR channel. There is a PCI bus over here through which this switch or other IO resources might be attaching, but there's no memory there right now. Okay. Now, as things move forward, right? So hardware industry and customers, no problem is left unsolved. So there is bottom-up innovation going on in the hardware world for the last couple of years on something called Compute Express Link, or CXL for short, which is an evolved PCI bus. It starts with PCI generation 5 at 32 gigabits per second, and with Intel Sapphire Rapids CPU, which is now out there. And now you can attach memory as using CXL as an expander. So you don't have to just attach to parallel buses. I'll show you a diagram of how first expanders look like. And then later, as pooling and switching take off in CXL generation 2 and beyond, you'll be able to attach memory in such a way that it will be on a fabric, and you can start to get around some of the stranding and such things. Okay, so then the software questions will arise. Okay, so but why could we not do it earlier? Well, because PCI bus, right? All of I worked on InfiniBand and PCI Express came out of it. InfiniBand was split based, but when PCI Express broke out, PCI Express, interestingly, even though it uses that wide serial link, right, 4x or 16x or whatever of serial links, it actually did not embrace InfiniBand's link level architecture. So it's not a pipeline switching technology like InfiniBand is. PCI Express says transport layer packets are out. Okay, so it's more like PCI in that respect. And you could not carry memory traffic because if you were a little memory traffic, which is latency sensitive, and an IO traffic crossed in front of you, well, a whole packet will cross. And so you could not meet latency requirements because you would have very variable latencies. Now, what they have done in PCI Express 5 for carrying CXL to arbitrate and then multiplex links for both memory and IO traffic. They have three different protocols. There is the old CXL protocol. The old PCI protocol is called CXL.io. And there are two new protocols called CXL.mem and CXL.cache that are carried on top of that PCI generation 5. And the old IO packets are no longer the threat because they're broken up into these 528-bit flow digits that, in the worst case at 32 gigabits per second, the nastiest thing that will cross in front of you is one of these 528-bit flits, and that's 13 nanoseconds. If a few of these go along, you are still in the kind of latencies that can be called memory latencies. Okay, so there are many innovations in CXL, too tight a constraint today to go through everything, but CXL is taking one of the more popular interconnects, IO expansion interconnects, and now making it possible to start to move memory away from the CPU and into this disaggregated realm where someday it will become an unstrandable resource. And then, software will turn that into software-defined memory. That's the hope. Okay. So things like expanders, pooling, disaggregation, this type of thing is coming in our world. Okay. So you can start to see that in the little cartoon diagram that instead of attaching memory just across these parallel buses, now you can start attaching memory across serial links, which is these wide serial links, which is PCI Express Generation 5, carrying CXL protocols. And now, you can have things like coherent accelerators, but most important and most interesting use case to the industry is that you can now start to attach memory buffers on the PCI bus. So, instead of going from 512 gigabytes to full terabyte, you can now say, hey, midlife kicker, I can add another 128 gigabytes on PCI bus. And then if I need to give that server another sort of, 60s or 70-year-old kicker, then I can go with another 128 or 256, depend on cost. So it gives more flexible way of deploying memory. You can have slower memory. So even though the CPU might insist on DDR5, you can attach DDR4 memory here, which might be recycled from old servers, for instance, or, might not require a PMIC on the DIMM like DDR5 does. For whatever reason, this could be a cheaper form of memory compared to what you would be attaching there. And then, as things move forward in CXL2 and beyond, you start to get these switches, such as, old memory companies are building, but there are now new ones like Elastic's Cloud and other who are building low latency CXL switches. And you will get these things called disaggregated memory nodes, which might even have a little bit of a SoC in front of them that can carry a little bit of compute. Because think about it, you'll be sitting, as you get to expanders, you will have an extra 60 some nanoseconds of latency. As you start to get over here, you will start to have double or triple the latency of local. And so at that point in time, it might make sense to not just do load store traffic, but to think about maybe having some compute gravitate to the data. So there we see some emergence of compute over here on these disaggregated memory nodes. Okay, and in fact, that's the rest of the talk will focus on that a little bit because that's where my head is at. Okay. So, the hope is that now uh, memory will move from being this bespoke, deployed, and uh, eagerly provisioned, and other evil things about memory we talked about, that kind of ugly resource, to something that is more friendly, both in terms of economics and consumption. So, meaning economics of both procurement and consumption. So it's configured to host by some things that look like fabric managers. So, the fabric manager concept also comes from InfiniBand, that you'll have some kind of management utility that crawls the fabric, much like, PCI uh, uh, walking is done by operating system PCI modules or BIOS PCI modules. And then out of that, capacity is stored out to hosts, containers, or applications, depending on the level at which that management software lives. And we will start to get this idea of far and fungible memory versus bespoke in server memory that we used to have. Okay, so this is a dream of CXL people, and there's very good interest from both vendors and customers, and a lot of activities going on in the industry that we are in the thick of. Okay. And so in some sense, right now, there's a couple of ways to think about it. You can keep thinking about it in terms of hierarchies, that you will get, inclusive cache type tier, which will be a far memory tier, which will be cached in front in DRAM. Or you can start to think in terms of, well, I'll have a little bit of fast memory with my CPU. And then on the side of that, as a sidecar, like in a flat view, like the new Linux component called heterogeneous memory management takes that view. It's just another type of memory in the data center. Okay, so now what's happening is that Linux and EFI BIOSes and ACPI and these specifications are now evolving, co-evolving with CXL to start to understand DCD, which is dynamic capacity detect. Okay, heterogeneous memory. Um, uh, you know, various tables that are created and populated by BIOSes, as opposed to being statically populated on the initial crawl, are now starting to understand that you will have dynamically created capacity that will become available because of configuration actions taken on these CXL memory devices, as in the form of hot plug address ranges. Okay, so the idea of hot plug memory, which is tax friendly, and you can use it just like memory, but it's becomes more of a fluid and fungible resource compared to in the past. Okay, this is the basic idea of software defined memory, which we have wanted but did not have. Okay, and so the stack is emerging. It works with other existing things that were in the stack previously, like our good old friend HWLock, which can crawl these things, collect latency attributes of the different types of memories that are available. This could be a GPU with HBM, which would be the lowest latency option you could discover, very traditional DDR DRAM, CXL DRAM, which is one hop away inside the server, uh, something like Z-swap memory, a portion of DRAM that has been set aside by using Linux configuration to be compressed memory. You could have CXL DRAM that is many hops away, or you could have compressed CXL DRAM by using, not only that our memory, but also a processor that's with it, to not just keep the memory there, but keep it compressed and or encrypted. Okay, and then this new module, the HMM, has been contributed by NVIDIA and others into Linux. It's been upstream. It allows applications to drive down policy on allocation and migration, and exposes high-level abstractions so that pointers are valid no matter whether they are in traditional host memory or what was traditionally device memory. That distinction starts to blur, so you don't have to have malloc for host memory and a specialized kind of driver malloc for driver managed memory. You start to get more of a uniform view of memory from applications, where that memory is allocated and where pages or other assets in memory are migrated is more a policy-based decision rather than a decision made upfront. Okay, so everything starts to be approached that ideal of goodness that we have seen in software-defined and dynamically uh, optimized data and compute in the rest of the assets. And this continues now from here. So we will, with CXL2 and 3, we will start to get these things called multi-host, multiple logical devices, where this kind of memory, like I showed in my cartoon, will be across a switch, and there will be hardware cache coherence, and if you need it, and it will be a dial by range type of coherence, as well as you will be able to dial capacity and bandwidth by choosing how those address ranges are strided across the different, in the same way we do ranking and banking, you'll be able to configure this CXL pooling and switching components to stride across those memories for creating dial down the dial up or down the bandwidth per capacity. Okay. So, the work has already started, and people like Microsoft and others are starting to publish their papers. So in ASP+ 22, Microsoft shared a very nice paper on CXL pooled DRAM where they will place their code pages. Okay, and they estimated that they will save about 10% of their total memory cost by just placing code pages in CXL memory that can be shared across 16 or 32 servers. Okay, so this kind of thing has started, and given the cost of memory as the #1 bill of materials item, there is excitement that even 10% of that is a very, very large number when you have 100,000 servers per data center, and something like 350 or so data centers for these big cloud players. So for them, this is actually big numbers when you do the math. Okay, and then like I was saying that when memory goes at a distance, then near memory processing will receive a boost because function will start to gravitate to data in the presence of high latency. And so compression is but the initial example. Other kinds of functions, your memory poisoning, zeroing, RAS functions, like integrity-oriented functions, they will start to, you will not want to use CPU load and store instructions to manipulate that memory on the other side of a long wire, okay, is what I'm saying, okay? So eventually, things like machine learning and databases will start to do database function push down. So let me give you an example, skip over this slide and talk about, what happens with data at a distance, which is accessed from many servers, and, in the age of domain-specific architecture, those things that access that pooled resource could be CPUs, GPUs, FPGAs, CGRAs, or any of the DSA flavors that we can describe in 3-letter acronyms these days. And then naturally, some of these optimizations, like we'll have to actually define what we mean by data gravity. We'll have to make it possible to take functions that manipulate data structures that define using virtual address space pointers like graphs and such to the device so it can operate on it. Today, the memory device only sees bits in physical address space. It doesn't know where the pointers are. So even if you tell it to compute a convolution, it could not, okay? And we go through the details of that. And so the idea is that, in these optimizations, no matter what you do in software, you want to make sure that this is still memory. So unlike storage, we will not be able to insert software in the entire data. We'll have to let load stores carry over the wire. We have to largely stay out of the way of coherence traffic, but somehow magically inject software at just the crucial points so we can define and deliver software-based value in this environment, and do that using uniform APIs that work with pre-CXL and post-CXL distributed and disaggregated deployments, because technologies such as this, will be a long time rolling out. And so there will be all kinds of mess out there in terms of infrastructure at various stages of overhaul in the next few years. Okay, so at Elephance, I want to take now just maybe 8-10 minutes, and then I'll close out with 8-10 minutes for questions. Is we are building a device side OS that runs over here in front of these disaggregated memory nodes and manages this memory, and then runs wherever you have these disaggregated memory nodes, and with the idea that it creates for memory what S3 did for storage, create self-contained objects and expose relationships between those objects as pointers that are valid with every compute. So they are valid with this compute, but if another one comes along and wants to work with the data that's in this memory, he doesn't have to go back to this guy and say, what is the directory and home node services for making sense of this pointer? Actually, inside every object, we bury something called a foreign object table that allows this to be efficiently interpreted by another CPU, with the idea that we'll be able to independently scale compute and data, which is the holy grail we are seeking in software-defined memory. But if you choose to cache these objects back at the host, the programming of MMU and EPT entries or VTX entries on that server so that you can efficiently work with these objects in x86 memory or ARM memory, we have proven that you can do that, okay? So the benefit of this is that, with memory objects, your metadata and indexing burden goes down, that you have self-contained context that has been rescued from the CPU, like instead of requiring page table entries and virtual to physical translation, which is trapped in a process and processor today, it has been rescued out so that it works with every processor and not just Intel or x86 processors, but with NVIDIA GPUs and other things as well, okay? So this idea of self-contained objects that have very efficient language bindings that can be worked from Rust and Python and such languages is what my company is working on. So let me give you a quick example and then close out. Okay. So you all, are familiar from your signal processing class on how basic convolution works on traditional data structures, such as images, like two-dimensional images. You calculate the value of a point by looking at the value of all its neighbors, and you can do simple things like averaging, or you can do complex things like Chebyshev polynomials, right? So in graphs, there is a similar idea, but graphs are not as regular as two-dimensional images, right? In a graph, a node can have one neighbor, or it can have a million neighbors, okay? So, you represent graphs using pointers, and graphs can represent compute like neural networks and query plans and data integration plans, or graphs can represent data such as, user data that goes into recommender systems, or supply chain data, or other sparse forms of data. In this day and age, pretty much all the computations that are challenging infrastructure in terms of scale today meet this property that both graphs represent both compute and data. Okay, so my company, Elephance, actually focuses on this class of applications with graph structured data and graph structured compute, and delivers the advantage of being able to offload things like convolution to memory. So if you compare, right, what would it take to calculate a convolution in the graph at node 3, you would have to go chase its neighbors. In the neighbor, that you would have to go to the structure offset at which there is the right property, then retrieve the value, communicate that back, communicate the polynomial on that value. And then if it was a polynomial of degree 2, that would not be enough. You'd have to go to the neighbor and neighbor's neighbor. So who uses the stuff? Things that do page ranks or random walks, or people who do real-time supply chains, real-time healthcare. They are doing petabyte scale graphs. In fact, their small benchmarks are like 38 terabyte benchmarks. And last year, in the first half of 2021, $500 million went into companies that build these in-memory graph databases like Tiger Graph and ArangoDB. And you can't even list all of them. There are so many now, okay? And enterprise knowledge graphs is all the rage, and it's not just for applications, it's also, Diffbot and Menlo Park is building a big competitor to Google on crawled data queries. And there's all kinds of interesting work going on in software around things like this. But if you use traditional CPUs to chase the pointers, then retrieve the neighboring node, retrieve local property, calculate filter polynomials, you will drive yourself nuts at a far memory distance, because you'll have many round trips. All the data you retrieve will be wasted because you need just a few values from the cache lines and pages you retrieve. So your throughput will be low. You will end up polluting your caches and shooting down TLB entries and flooding your network. And you will end up with what Google calls rule of 3 penalty, which is you'll be constantly starving the front of your load store pipeline, because you will have finite load store outstanding, and you'll not be able to keep the load store pipeline busy because your CPU will actually starve your load store pipeline for work. Okay, this is what actually happens already, and it will just get much, much worse. Google estimated, based on a study of 50,000 servers, that roughly 1/3 of the cycles today are wasted on front-end stalls. Okay. Now, when you compare with, doing this work by offloading to disaggregated memory node, with having disaggregated memory node chase the pointer, retrieve neighbor node, locally retrieve local property, and calculate filter polynomial, he will just return you the convert value. This will result in low latency, high good port, and independent scaling of memory and compute, because data is self-describing. And it basically is like, what Parquet format and self-describing data did to storage. We'll start to see those things happening to memory. So let me keep moving and show you this slide that comes from a recent survey of large customers that were conducted by the Open Compute project, which is what kind of applications are memory bound today and stand to benefit from the deployment of CXL and Elephance technology, as we described. One is, of course, overcommit and hypervisors is the bane of general purpose virtualization. And then the other two culprits are databases and AI/ML. And, only some of them are latency critical, like, some workloads that very actively work with large amounts of data as their active working set might not be able to tolerate those latency. But for other workloads, they're capacity driven and they'll be just fine using this far memory if we can then dial the bandwidth properly. Okay, so just now moving into a little bit of market knowledge for you. So like I said, there are these things called EKG forum where people like United Health, Optum, and banks doing anti-fraud applications, and all kinds of companies now, as supply chains shift from just in time to just in case supply chains, right? Just in case supply chains with higher inventory. Everybody is thinking about real-time everything, real-time patient care, real-time supply chains, real-time fraud detection. And the in-memory part is just exploding. And companies like ours come in, they live between the memory where the big graphs and the big compute graphs are held, and they supply a standard interface into the compute tier where these queries are executed on EC2 instances that will hopefully be less of that upfront procurement of memory and more of that fungible procurement of memory. Okay, so that's the vision that we are working towards. I'll skip these slides. This is our differentiation, and I just want to point out something to you, that these ideas are not just for the future. We can actually go in, we can, for example, rent an X3BG instance in Amazon with a terabyte of memory, just run our software stack, which we call MEMOS or memory operating system, and we can start doling out memory as a service or even on existing slow networks. Now, most applications that are latency sensitive will not use that, but some that are desperate enough for capacity and don't care that much about latency will even use that. So we can go into business in pre-CXL world, we can expand our footprint in CXL1, and then be really big in CXL2. This is what we hope. So let me end with this slide, which is what's going to happen to the world of memory. Okay, so as I illustrated to you in the convolution example, we actually sat down with the VP of CUDA at NVIDIA, and we said, this is what we are thinking of doing. What do you think? And they said, interestingly, if you look at a data flow graph and think of three types of code that exists in computation: fluxy, branchy, and loopy. GPUs are very good at loopy code. You're going to take a little bit of memory and you're going to iterate on it to death, like machine learning training does. Okay? The Intel CPU with its big ass and very mature branch predictor is really, really good at branchy code. You don't want a little processor near memory to deal with very branchy code. It will kill itself to death because it doesn't have an iCache to speak of. It will just be constantly starved for instructions. But if you have fluxy code, in which a lot of data flows through a little bit of computation, like we have with aggregation, prefix computations, convolutions, some random walks. You can do that near memory very, very efficient. So in the future, the traditional memory that we have today is going to be supplemented by three forms of memory. One is far memory, which is how we are starting to see in CXL1. One is near memory, right? Like you have with HBM, and you will have HBM3, and many people who don't like DRAM and HBM will switch to more and more SRAM, co-packaged SRAM, all kinds of packaging driven HI type systems, heterogeneous integration type systems. And then the third will be this kind of computational memory for performing on data intensive workloads. And in fact, the winning combination is this far memory when combined with computational memory because of what I said. I said when distance is far, always doing load store is not the right thing. Function naturally wants to gravitate to data. And so not only is this the winning combination, it actually makes traditional functions like GPU and HBM more efficient, as our friends at NVIDIA noted. And this is what Elephance is now trying to have. Okay, I stop here. This is my contact information, and I want to leave at least a little bit of time for questions, Dan. Back to you. Okay.
Thanks, Pankaj. Highly appreciate your flexibility and recovering very quickly from sudden network death. It happens when you have far memory access. So we have a couple of questions that were typed in, and I also have some questions, and everybody else is welcome to ask questions. The first one comes from Gene Freeman, and the question is the lowest latency memory inside of the processor still SRAM?
Yes.
Okay. Question from Tom Coughlin. So is this a way to integrate accelerators close to far memory?
Yes. In fact, this is a very good question, because if you think about that, Tom, what does it take to compute with user data? Okay, so suppose I have a big graph, okay, and maybe I'm doing, finite element method, like, chasing cracks through nuclear stockpiles. Or maybe I'm doing one of these enterprise applications like enterprise knowledge graphs. If I go in the traditional way, and if I give my bits to that far memory, and I don't give it the ability to have that translation context, okay, how will it work with the virtual addresses? Now think about if I have a cluster, everything these days, if it doesn't scale, it will fail. So everything is scale out. So now the problem becomes which processor has translation context for which data? Because everyone has page table entries, everyone has MMU and EPT and VTX. And how do I find out whose context do I need to rescue? So we said, we are going to make data a first-class citizen of the network. We are going to the first translation context will be in the object itself. And maybe in a future version of this industry spotlight, we will do a deep dive on our MemOS and Twizzler work in terms of how did we engineer the foreign object table. But let me give you a quick analogy today, just in the interest of time. So, you might think that if you try to embed translation context into every memory object, then these translation tables will become as big as page table entries for all the memory in all the nodes, right? And will become untenable. But it's not true. So why is it not true? So, there are maybe 100 people in the seminar, and some of us are friends with each other. But if you look at any person's phone book, okay, there are only a few entries. We don't all have 100 entries containing everybody's phone number and everybody's phone book. So our Elephance memory objects are like that. The foreign object table only contains the full addresses with 128-bit ID and 40 some bit offset of those friends with which this object shares some outgoing bits, okay, and does not care about everything else. Okay, so when you have a pointer, which is in our case still 40 some bits, if the pointer is local, it just works like a local pointer on x86 or ARM or whatever. If it's a pointer to a foreign object, it resolves through the foreign object table. On our initial implementation, we have seen that if it's another object on the same, another pointer to a different object on the same CPU, it takes just a few nanoseconds to resolve. If it's a pointer to a foreign object table, it resolves through the foreign object table. On our initial implementation, we have seen that if it's another object on the same, another pointer to a different object on the same CPU, it takes just a few nanoseconds to resolve. If it's a object on a different node, it takes those few nanoseconds plus the time to route through the network. And in our papers that we have published in Hotnets, we have shown that we can program P4 programmable switches to route by ID very efficiently. Okay, so a lot of work is going on in this. This is not fully developed. Some developments related to our MemOS networking are still in progress, but it's very promising. Tom, did I answer your question?
Actually, he has the second part, so let me read it.
Okay.
Thank you, by the way.
Pankaj, do you see this farm memory remaining mostly DRAM, or will other persistent memories become common?
So I think they want to become cheaper memory. Unfortunately, the best candidate we had for that cheaper memory, which is 3D Crosspoint, has a fundamental limitation that we knew about since 2015. Crosspoint memories have a limitation because after 3 or 4 layers, every layer is lithocritical. It's not like NAND where you just deposit, and in a single high aspect ratio etch, you can make all the devices in all the layers. So when you make crosspoint memories, your cost of manufacturing actually goes up non-linearly with the number of layers. This is why there is no third generation Optane right now. Okay, so we do need another memory, and maybe I'm too smart for my own good, and other people have better ideas, and they are just about to bring out a third generation Optane that is going to drastically increase layer count and prove me wrong. I hope that happens, but we have DRAM, DDR5 DRAM and DDR4 DRAM and compressed and uncompressed DRAM, and every trick in the book, like compress objects, not cache lines, and every other trick we know how to trade off compute cycles uh, for capacity is being used with DRAM. So the short answer is yes, DRAM in the near term.
Okay, very related to your question, although I think we may need some help from the person who asks. In your experience, is NVRAM a real competitor for persistent memory? Although NVRAMs have an inherent size constraint.
So NVRAMs, I posed this kind of question to a very famous and very wise person. His name is Eric Brewer. He's VP of infrastructure at Google, but he is famous for having founded Inktomi and sold it to Yahoo in the first wave of internet. Then he was Berkeley professor. So when he was Berkeley professor, I asked him about persistent memory. And instead of answering my question, he asked in the form of rhetorical question that if I have data and I throw it to the four winds and it sticks in enough places, do I have persistence? Okay. What he was saying was that persistence and non-volatility are two different things, that persistence and replication go hand in hand. And you can think of it like space-time. So persistence due to non-volatility is like separation in time. Your CPU wrote something, then it died, it came back after a restart or some other delay, and now it wants its data back. And if the memory was non-volatile, it can have the data back at the same point in space. But you can also use something other than non-volatility and simply just migrate the data, replicate it elsewhere. And if you go down and that data moves outside the blast radius or outside the fault zone of the last CPU that wrote it, you can just send a message to the other guy or do an RPC or do an RDMA read and say, give me my data back. Same effect. Both are persistence. One is in space, one is in time. And actually, one of the optimizers that Elephance is developing takes this view of space-time, of persistence, and adds a third dimension called recomputation, okay? And asks the question, what is data gravity? Okay, is there some warp in this three-dimensional space of space, time, and recomputation in which we can define data gravity, okay? So these are sort of the more esoteric theoretical type questions that we are working on for our data and compute placement optimizers. But enough said about that. Maybe give chance for one more question.
Okay, the same person had another part of the question, and that is also, has there been any past research on pointer chasing used in MemOS? he's familiar with the work done at OpenFAM, but beyond that.
Open.
FAM, fabric attached
Okay.
memory.
Can you please remember to send me email to follow up? The work on pointer chasing is actually as old as the definition of memory wall, as far as I can remember. I think either at UVA or at Stanford, there was some early work on offloading pointer chasing to memory. But unfortunately, they did not have the genius of Daniel Bittman, who wrote the Twizzler operating system, which is precursor to MemOS, and created memory objects. I think all this kind of thing will become much easier with memory objects than it was previously.
Okay.
The idea itself is old. Yeah.
Any other question by the audience here? We should probably stop pretty soon. We're 4 minutes over. I am allowing more time because of the interruptions. Okay, so my question is, Pankaj, where do you find the balance or the trade-off between very intelligent, more general purpose MemOS and something that is very limited in functionality but robust, such as operators that convert? You seem to be inclined more towards former rather than latter, with all the intricacies, benefits, but drawbacks as well.
Yes. In fact, we were always very concerned that we had set our sights too high in the stack and that we would have to end up integrating with databases and, like any scale Ray or, Kafka or this type of things. When, all we have is C code, we don't even have Java in the beginning. So how will we address our market with so much gap between where we are and where the stack that we need to intersect? Okay. As I started to work in the industry on the SOCs that are actually coming out, what we found is that as an organization principle and as a way of creating manageable management of large scale memory, like petabyte scale memory pools, actually memory objects is a really great organizing principle for keeping metadata small, indexing small, or even very routine near memory use cases like the RAS use cases, compression use cases, and zeroing and poisoning use cases. So over the last 12 months or so, our relevance has actually gone from being only CXL3 and very relevant to only databases and such things, to being relevant even in CXL1 and CXL2 timeframe on very near-term use cases and very simple use cases of the kind that you are hinting at, Dejan.
Okay. Well, with this, I thank you very much, Pankaj. You can always reach out to Pankaj. This video with cut intermission breakages will be available shortly online.
I just want to say one last thing, Dan, that Elephance is raising. There are a lot of strategics who are interested in investing in us, but we are looking for a lead investor. So the timing of this was great. I hope one of you wants to lead our seed round. Thank you. Thank you for attending.
Thanks, everyone. Bye.